See. So next concept which we are studying is motional EMF. EMF produced because of motion of the conductor. Motion in the sense movement of the conductor. Are you able to understand? Sima. Previously we studied if flux linking changes, if flux linking the coil changes, EMF will be induced, no? EMF will be induced. This is the first method of producing the flux, producing the EMF. Now we are studying second method. What is that second method? Whenever conductor cuts a flux, then also EMF will be induced. See, magnetic lines of force, they will be like a stretched strings in a musical instrument. Musical instrument lo strings చూసింటారు కదా, వీణ, violin, బాగా లాగుంటాయి. So magnetic lines also will be like that. Okay, ma? See, for example, this is magnetic lines or magnetic field you can call. So it is entering the board, no? Now in this magnetic field I am taking a conductor. So this is a conductor. Okay, ma? Now this conductor, I have to move this conductor in this field such that it cuts these magnetic lines of force. Even magnetic lines hai kada. So if these magnetic lines are cut by this conductor, then EMF can be induced. And if it is a closed conductor, current also will flow. Okay, ma? Now see. So if I move this conductor downwards, conductor I am moving downwards. If this is the conductor, I am moving like this. Okay, ma? EMF will be induced or not? No. Why? Lines, they are not cut, no? If I move the conductor in upward direction? No. If I take this conductor out of the board? No. If I take this conductor inside the board? No. Mariala? So if I move this conductor in this direction, clear, ma? Then this conductor will cut the magnetic lines of force. Are you able to understand, ma? See here, what is the direction of magnetic lines? They are like this, perpendicular and inside the board. This is my conductor. So if I move like this, I cannot cut this line. If I move like this, I cannot cut this line. If I move like this, I cannot cut. If I move inside also, I cannot cut. So what is the method of cutting this, what you call magnetic line? I have to move in this direction. Okay, ma? If I move in that direction, then flux can be cut. Okay. So therefore, now see, ma, if I move this conductor in this direction, what happens? Let us see. Okay. Now in this conductor, charges will be there, no? For example, if I take one electron, electrons will be there in a conductor, no? Okay. Now if I am moving this conductor with a velocity of v, it is an example of charge entering magnetic field at an angle of 90 degrees. Correct only, no? Magnetic effects of current we have studied, no? So this is a charged particle. Electrons, many electrons will be present. I am taking a single electron. So if this electron is moving in this direction with a velocity of v, what is the direction of magnetic field? Inside the ball. So what is the angle between velocity vector and magnetic field? 90 degrees. So it is an example of charge moving in a magnetic field at an angle of 90 degrees. Then it will experience magnetic Lorentz force, no? Gurtunda idi? For example, if this is the direction of B dash, and if this is the direction of charge, clear, ma? Moving with a velocity of v plus q, okay, ma? At an angle of theta, then this charge will experience some force that is given by f dash is equals to q into v dash cross b dash. Do you remember this one? Magnetic Lorentz force. So place your right hand on velocity, rotate towards b dash. What is the direction of force? Perpendicular and out of the board. Same concept is I can use here also, no? Are you able to understand, ma? So this is a charge moving with a velocity in a magnetic field at an angle of 90 degrees. So definitely this electron also will experience some force. Now by using this relation, can you say force will be in which direction? Try to say the direction of force. This electron, which is present in this conductor, if it is moving in this direction, then it will experience a force in which direction? By using this relation. Think. कई को बोलो, करे तो ऊपर को जाता है ना, ये रोटेट होता नहीं है. This cannot rotate. It is present inside the conductor, no? It is not a free charge. Clear, ma? See here, Q into V dash cross B dash. So place your right hand on V dash. What is the direction of B dash? Inside the board, no? B dash. What is the direction of thumb? Upwards. But it is wrong. Niche kai ko. See, but this is the direction of force if it is a positively charged particle. No, electron is what kind of particle? Negatively charged particle. It will experience force exactly in opposite direction. This is the direction of magnetic Lorentz force. Are you able to understand, ma? So this equation we have studied for positive charges. No, electron is what kind of charge? Negative charge. So just you have to reverse the direction of force. Okay. Now can you say, when electron experiences force in downward direction, then what happens? Torque ekkada produce ayindra akkada. See, when this electron experiences force in downwards direction, what happens? మిమ్మల్ని ఎవడన్నా పట్టి లాగితే ఏమవుతుంది? కోపం వస్తుందా? ఇదేమో లాజిక్ రా. साहब में खींच तो खिंचक जाती जी. ट्राई करेंगे एक बार. अंते కదా. So all these electrons they go and deposit at the end of the conductor. That's all. All the electrons they are experiencing downward force, no? So what happens? So all these electrons they go and deposit at one end of the conductor. Are you able to understand? So this end of the conductor, it will become negatively charged body. Okay. If one end is negative, automatically other end will become positively charged body. This is what happens. Are you able to understand? So positive charges are at higher potential, negative charges are at lower potential. So potential difference has developed. No? That's it. That is the method of developing EMF. Are you able to understand? No? Very simple concept. So therefore what happens? Due to magnetic Lorentz force, ఆలోచించండి అంటే మరీ ఓవర్గా ఆలోచించి ఏందేందో చెప్తానారా మీరు. ఎందుకు అవుతుంది? లాజిక్ కరెక్ట్గా ఉన్నప్పుడు సిల్లీగానే ఉంటుంది మరి. సో డ్యూ టు మ్యాగ్నెటిక్ Lorentz force, all electrons get deposited at one end. Okay, ma? Other end becomes positively charged. Okay, ma? Therefore, a potential difference develops in the conductor. So are you able to understand, ma, why potential difference is developing here? Clear, no? So whenever a conductor cuts a flux, immediately electrons get deposited at one end, positive charges will get deposited at the other end. So this is at higher potential, this end, and this end is at lower potential. So therefore an EMF gets developed in the conductor, and if it is a closed conductor, current also will flow because EMF is there. No? So this is behaving like what? This is behaving like this kind of body. Okay, ma? This conductor is behaving as if some battery is present. Okay, battery unte ela untundo ala ee conductor behave chestadi because there is a potential difference, no? So on this side positive potential, here negative potential, behaves like a battery. And this kind of battery you can call it as a virtual battery. What is meant by virtual battery? Virtual battery means వర్చువల్ స్టూడెంట్స్ లాగే ఉంటారు కానీ బుర్రలో ఏముండదు అనమాట. సో ఇది కూడా అంతే. వర్చువల్ బ్యాటరీ అంటే బ్యాటరీ ఏమి ఉండదు అక్కడ, బట్ It will supply potential difference. అది చెప్తూనే ఎవరు నవ్వినారో వాళ్ళే వర్చువల్ స్టూడెంట్. कहीं प्रोड्यूस करता है स्पीड पर डिपेंड होता है. हाउ स्पीडीली यू आर मूविंग, व्हाट इज द स्ट्रेंथ ऑफ मैग्नेटिक फील्ड. इट कैन ऑल्सो प्रोड्यूस ह्यूज करंट. ओके, ये करो को जी बाबा ये सब करते हैं, सो कैसे करते हैं समझते हैं. वो प्रोडक्शन, ये ऑपरेशन. ओके मा, नाउ सी हियर. हाँ, करंट कुछ ऐसा प्रोड्यूस करोगे को इसे ढकल ना सको ना, तुम्हें वर्ड को ढकल ना होता, उसे एक सोर्स ऑफ एनर्जी होना सोचना. सीमा एनर्जी यू कैनॉट क्रिएट, यू कैनॉट डिस्ट्रॉय. इसे तुम्हें ऐसा लेके जाना का तो somebody should apply force on this one. उसे फोर्स अप्लाई करना. हाँ, वो मिशन को चारा क्या डालते तुम्हें, तुम्हें ढकलना है तो खाना वो भी फ्यूल इच्छना. ఏ వర్క్ మీరు చేయాలన్నా ఎనర్జీ అవసరమే. డైరెక్ట్ మనం ముద్దులండి ఇవన్నీ చెప్తే పిల్లలు బయట. ఓకేమా, ఇస్ ఇట్ క్లియర్? సో నౌ సీమా హియర్ ద ఇండ్యూస్డ్ ఈఎంఎఫ్ ఈజ్ గివెన్ బై E is equals to BLV. This is the equation. Clear now? Here the amount of EMF induced is given by which equation? BLV. What is B here? B is strength of magnetic field, L is length of conductor. Length of conductor in magnetic field. Okay ma? And V is velocity or speed of the conductor. Are you able to understand? This is magnetic field. So EMF depends on how many factors ma? It depends on strength of magnetic field, what is the length of the conductor, and what is the speed of the conductor. Okay, so this is the equation. So previously we studied one equation, no, E is equals to minus d pi by dt. Here also this is also same, but here flux is EMF is produced because of change in flux, and here EMF is produced because of cutting of the flux. Two methods of producing EMF. Are you able to understand? Okay. Now Sima, for example, so sometimes questions can be asked like this also. Okay. So inside this magnetic field there is a semicircular coil. This kind of coil is present. Radius of the coil is 10 centimeter. Are you able to understand now? Strength of the magnetic field is 2 Tesla. Okay, and velocity of this coil is 10 meters per second. Then find the EMF produced. Can you calculate? Okay, so this is a semicircular wire conductor which is moving in this direction with a velocity of 10 meters per second. This is the strength of magnetic field, and this is the strength of, and radius is 10 centimeter. Now can you say how much EMF will be induced in this coil? Anybody? Huh? BLV यूज करेंगे कहते, R वैल्यू कहता, L कहता. No. Sima, here you should not take this total length ma. If you take this total length, then it is circumference 2 pi r divided by 2. Okay, we are not supposed to take that length. We are supposed to take straight line length only, because that is the effective length which is responsible for cutting, no? Huh? 5 कैसा होता है जी? Straight line length कितना है इसका? 10 plus 10 20. Diameter will become 20, no? So what is the point here? We have to understand. Point is that, clear ma? So only straight line length is considered. Okay ma? Which length we have to consider? Only straight line length should be considered. Therefore L will become 2 times of radius, nothing but diameter. So 2 into 10 is how much? 20 centimeter. So it is 20 into 10 power minus 2 meter. Therefore, EMF induced BLV. B is 2, length is 20 into 10 power minus 2, velocity is 10. Okay, ma? So totally how much? 40, 400, 4 volts. This is my answer. EMF induced is 4 volts. Are you able to understand? I will give you one more question, try to answer it. So for example, this is magnetic field. Okay, ma? And this is the conductor. It is moving in this direction with a velocity of v at an angle of theta. Length of the conductor is L, strength of the magnetic field is B. Now can you say what is the EMF induced? Anybody? Why we have to take cos theta? See, now this conductor, it is not moving like this, it is moving like this. Okay, so what I can do, I can split this velocity vector into two components, no? So split this velocity vector into two components. So this is v cos theta and this is v sin theta. So in this direction it can move with v cos theta, in this direction it can move with v sin theta. Which velocity is responsible for cutting the flux? V cos theta is responsible. Ila vellatam valla flux cut avvadu kada. Only if it is moves in horizontal direction, then only it can cut the flux. So therefore I am supposed to take v cos theta only. Okay. So therefore what is the point here? I can write a point is that only because of v cos theta, clear na? Conductor cuts the flux. Conductor cuts the flux. Therefore, E is equals to B into L cos theta, B into L into V cos theta. So this is my equation to calculate EMF induced. Are you able to understand, ma? So this concept is called as motional EMF. So EMF induced because of motion of the coil. Are you able to understand? See, ma. Let us see one more condition. See here, if this is magnetic field, this is the coil. Okay, ma? So if this coil is moving in this direction with a velocity of v, find out EMF induced. Length is L, breadth is B, and strength of magnetic field is B. Anybody? No. ఆలోచించి చెప్పండి. Think very carefully and try to see. See here, this is a coil moving in a uniform magnetic field with a velocity. In the morning class, what we discussed that flux linking is constant. Flux linking is constant. No? ఒక magnetic line leave అయితే ఇంకోటి enter అవుతుంది. So flux is a constant. If flux is a constant, d pi, change in flux is 0. So EMF induced also d pi by dt value will be how much? See, this is one method of explanation. Okay, now we will try to understand this one by using motional EMF. Okay, this is first method. Now we will try to understand this one by second method, which is called as motional EMF. See, ma, here I will divide this figure into A, B, C, D, 4 parts. Okay. Now what about AB? It is also moving with the velocity of v, no? But this AB, can it cut the flux or not? It cannot cut the flux. See, my magnetic lines are like this. It is moving like this. Will it cut the flux? No, so EMF induced is 0. So EMF induced in AB will be how much? 0. Because it cannot cut the flux. Okay. What about EMF induced in DC? So EMF induced in DC also will be 0. Because it is also not cutting the flux. Are you able to understand now? Now what about magnetic field induced in AB? Will it cut the flux or not? This one will definitely cut the flux now. So therefore what is the EMF induced in AD? Okay, ma? BLV is the formula. No? B, length of the conductor is small b and velocity is v. Okay. So in this wire definitely EMF will be induced because it is cutting the flux. Similarly, what is the EMF induced in BC? BC. Same, strength of magnetic field is B, length is B, small b, velocity is v. Okay. But what we are saying total EMF induced is 0. How can you explain? But in here also EMF is induced, here also EMF is induced. Then how can you say total EMF induced is 0? How can you say? Anybody? Sima, in this wire and in this wire EMF is not induced, but here also EMF is present, here also EMF is present. But why I am saying total EMF is 0? This is according to Lenz's law. Now I want according to motional EMF. Anybody? Very simple. This EMF will be cancelled by this EMF. That's all. That's all. See, see this circuit how I can draw. Say this circuit I can draw like this also. So it is as if battery is present here also. It is as if battery is present here also. This is also a battery of EMF E. This is also a battery of EMF E. They are connected in opposite polarity. Are you able to understand, ma? Positive connected to positive, negative connected to negative. Total EMF becomes 0. Same polarity in the sense their potentials are getting cancelled, no? Okay, ma? Positive connected to positive, negative connected to negative. EMFs gets cancelled in. Okay, so therefore I can say total EMF is 0. That is what is happening. But definitely EMF is produced in this wire also, EMF is produced in this wire also. But both EMFs they will get cancelled with each other. So therefore both EMFs get cancelled. Okay. See, we know battery connection, if see for example, if I give battery connection like this, then can you say what happens? This is EMF, this is EMF. Now what happens? Here total EMF I can say E plus E to E. That's all. No? Now here negative connected to positive. Negative terminal connected to positive of the next terminal. So EMFs will get added up with each other here. But same connection if I give like this. Okay. So this is one battery, this is another battery. EMF E, EMF E. Now what happens? They will get cancelled with each other because they are connected in opposite polarity. Opposite polarity only. Huh? Positive, negative. This is same polarity. But if connected like this, then it is opposite polarity. They will get cancelled with each other. That is the reason why total EMF is becoming 0. Okay. So here total EMF will be how much? E minus E will become 0. That is our answer. Fine? Okay. See, ma'am. Now here we are trying to find out what is the direction of induced EMF and what is the direction of current by using Fleming's right hand rule. In which concept we are using this one? In motional EMF. Motional EMF means what? When conductor cuts the flux. Clear? See, here these directions. These are the two magnets and this is the direction of magnetic line. They travel from north to south. No? Are you able to understand? Now inside this magnetic field we are placing a conductor. And how I have to move this conductor so that it can cut the flux? This conductor no nenu ela move cheyali. This is the direction of magnetic lines. So, see, this is the direction of magnetic lines. Conductor is like this, no? So I have to move this conductor either in upward direction or downwards direction. Then it will cut the magnetic lines. Are you able to understand? So therefore, that direction of induced EMF is given by Fleming's right hand rule. What does forefinger indicate? This is forefinger. Forefinger indicates the direction of magnetic lines or direction of magnetic field. Okay? And thumb gives the direction in which you are moving this conductor. Okay? See here what is happening. This is the magnetic line. Conductor is like this. If I cut like this, then also it will cut the flux. No? If I move this conductor like this, then also it will cut the flux. So that direction of movement of this conductor is given by thumb. Okay, ma? Then what does middle finger indicate? Middle finger indicates the direction of current. That's it, very simple. Are you able to understand now? So therefore, forefinger indicates what? This is forefinger. Forefinger indicates direction of B dash. Direction of B dash. Clear now? Thumb gives direction of motion of conductor. Okay, ma? In which direction we are moving the conductor. This is thumb. Okay? And this middle finger, it gives direction of current. Direction of current and EMF both are same. Direction of current, or you can say direction of EMF also. Current will flow in the direction of EMF only, no? That is Fleming's right hand rule. Okay, ma? So it means that if thumb is outwards, no? So if I move this conductor out of the board, then current will flow in this direction. What is the direction of current? This will be the direction of current. That's it. Okay? If conductor is coming out of the board. Are you able to understand now? So closed conductor coming out of board. Right. See this application. Here previously we studied if this is the magnetic field and if conductor moves in this direction with a velocity of v, then it is cutting the flux, no? Then EMF will be produced. Now here what is happening around this axis, we are making this conductor to rotate. It is rotating in a rotational motion. Okay, ma? Now EMF will be produced or not? Produced. How can you say? It is cutting magnetic lines, no? So, this is the conductor, okay, and it is rotating like this. Definitely it will cut magnetic lines, no? So in this condition, what is the equation of EMF induced? That I want to find out. Are you able to understand? Now first of all, can you say EMF direction will be how much? Now what will be the direction of EMF induced? Okay, so you always check electron direction. This is the electron, no? Electron. Okay, so magnetic Lorentz force Fm dash is equals to Q into V dash cross B dash. Okay, consider velocity is like this. So V dash, B dash. This is the direction in which positive charge will experience force. Velocity, see, when rod is in this direction, velocity is in this direction only, no? So V dash cross B dash, positive charges will experience force in this direction. But electron is a negatively charged body. So all the electrons, they get deposited at one end. All the positive charges, they get deposited at another end. Okay. So it is as if I can say this will be the direction of EMF. I can say like this. Clear, Nama? Why? Because on this side it should be positive, on this side it will be negative. Are you able to understand? And if I close this one into a conductor, if I close this one, if I close the circuit, then current should flow in this direction. Because current always flows from positive to negative. Are you able to understand now? Okay. So direction of EMF we have understood. Now I want an equation of EMF. See how I can calculate. When conductor cuts the flux, motional EMF is given by BL, we know BL. Now because it is moving in a circle of radius r, what is its radius? Radius is nothing but the length of this conductor, no? Clear? So E can be written as B into, instead of length of the conductor, I can write R. Now can you say what is the velocity of this conductor? Velocity of this conductor is how much? Velocity. Sima, if it is rotating like this with an angular velocity omega, this point's velocity is 0, no? This is at rest position. Axis is at rest position only, no? Now this point will have certain velocity. So velocity is given by omega into r. Do you remember? Tangential speed of a body is given by omega into r. So if I move away from the axis, tangential speed continuously increases because r value increases. In rotational dynamics we have studied this one, no? Okay. So here velocity will be lesser, here velocity more, this velocity will be maximum. Okay. At the axis velocity is 0, at the end velocity will be maximum. So therefore average velocity I can calculate, no? Average velocity is minimum velocity plus maximum velocity divided by 2. I can take like this also. Average velocity of the SIMA conductor does not have a constant velocity. Throughout the conductor, okay, velocity on the, no. Velocity is changing. So at the point of contact velocity is 0, at the highest point velocity is V. So better you take average velocity. Okay, ma? So therefore average velocity is how much? V divided by 2. What is V velocity at this position? At this position velocity is omega into r only, no? If this total I can consider radius of this wire or radius of this conductor, then V is equal to omega into r. Substitute here, or I will substitute small letters, or capital, anything is okay. I will do one thing, I will take this one only to be capital. Okay, capital R is equal to here. Now substitute. So E is equals to B into R into, instead of velocity I can write omega into R divided by 2. So therefore what is the equation I got? Half B omega R square. So this is the equation to calculate EMF induced if a conductor is rotating in a magnetic field. Magnetic field or rotate avutunnappudu, this equation we can use. Have you understood how we have calculated? So L is R. Velocity I have taken average velocity. Velocity is nothing but omega into r, no, by rotational motion, that I have substituted. That's very simply I got the equation. Okay. So this condition you will use in which concept? Sima, sometimes he will give question on fan. Fan is rotating. Perpendicular to the wings of the fan there is some magnetic field. Then what is the EMF produced? Definitely this is that condition. Wing of the fan, it cuts the magnetic lines. Directly you can use this relation. Half B omega into r square. Okay. Sima. So there is a wheel which is having 10 spokes. So consider this is a wheel which has some spokes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 spokes are present. So, and length of each spoke is 0.5 mm. It is rotating with a speed of 120 rpm in a plane normal to Earth's magnetic field. It means Earth's magnetic field, let us consider it is like this. Okay, ma? And this wheel is rotating like this with certain angular velocity. Then definitely each spoke will cut magnetic line, no? Each spoke will cut magnetic line. So EMF will be induced in every spoke. Okay. So therefore, if magnetic field strength is 10 power 4 Gauss, G means Gauss, then what is the magnitude of EMF induced? Already we have studied the equation, no? Okay, ma? So magnetic EMF induced in each spoke is equals to half B R square into omega. Already we have derived equation, no? Magnetic field is how much? 0.4 Gauss. Okay, ma? Sima, 1 Tesla is equals to, Tesla is the SI unit of magnetic field. 1 Tesla is equal to 10 power minus 4, 10 power plus 4 Gauss. Therefore, 1 Gauss is how much? 10 power minus 4 Tesla. So therefore B is equals to 0.4 into 10 power minus 4 Tesla. This is the strength of magnetic field. Are you able to understand? And what is the radius of each spoke? Radius is 0.5. Angular velocity is how much? Angular velocity is 2 pi f. Frequency is how much? Huh? No, frequency is not 120. Frequency is 120 by 60. Okay? Because RPM he gave, RPM, rotations per minute. But frequency is per second, no? So divide by 60. So therefore it is 2 hertz. That is the frequency. What is the angular frequency? Angular frequency is 2 pi f. Omega is present, no? I want angular frequency. So 2 pi into frequency is 2. So angular frequency is 4 pi radians per second. Clear? Now substitute all the values, that is our answer. Okay? So therefore EMF is equals to half into B value is 0.4 into 10 power minus 4. Okay, ma? Radius is 0.5 whole square. Omega value is 4 pi. Do this calculation, we get the value of magnetic flux, electric potential induced. 157 point, no. 6.28 into 10 power minus 5. 6.28 into 10 power minus 5 volts. That is the EMF induced. Fine? Okay. Same. So next topic which we are studying is self-inductance. See, this is a coil which is wound in the form of a spring, or this one you can call it as an inductor. Okay? Now to this inductor we are connecting one switch. There is a switch and there is a source of potential difference. Battery is present. Okay? Now if I close the switch, what happens? Current starts flowing. No? For example, this battery for this circuit, it can supply 5 amperes of current, for example. Now when I close the switch suddenly, current will be suddenly 5 amperes or it will increase in steps? Always it will increase in steps, no? Are you able to understand, ma? మీరు ఇక్కడ నుంచి కిందికి పోవాలంటే స్టెప్స్ నుంచి పోవాలి కదా, దూకరు. Same concept here also. So if you close the switch, current always increases in steps, but it will take a very small time. But definitely it will increase in steps only. So because it is increasing, current is variable, no? If current is variable, magnetic flux produced around the coil is also variable. So therefore, if flux is variable, EMF will be induced. Are you able to understand? Sima. So initially very small amount of current will flow. I1 is 1 ampere. Then very small magnetic field will develop. Now after some time what happens? 2 amperes will flow. So therefore the strength of magnetic field also increases. Now after some more time 3 amperes will flow. So therefore the amount of flux produced also will increase. Are you able to understand? So if flux increases, flux linking with the same coil also will increase, no? Okay, and if flux linking with the coil increases, what happens? EMF is produced. That's what we have been studying, no? Chapter starting nunchi dabba em kodta unnam manamu. If flux linking the coil changes, EMF will be induced. That is what we have been studying, no? So immediately if I close the switch, current increases. If current increases, flux increases. If flux increases, flux linking with the coil also increases. So therefore EMF will be induced in the coil. Are you able to understand, ma? So this type of induced EMF, what we call? We call it as self-induced EMF. Okay. Now can you say what will be the direction of this induced EMF, ma? This EMF will be in which direction? Can you say? Anybody? By using Lenz law. By using Lenz law, can you say what will be the direction of induced EMF? Opposite to the flow of current. Why? Yes. See, here current is increasing, no? Current is increasing. So this coil will develop EMF such that this current is opposed. Are you able to understand? Because that is the function of coil, no? Always it will oppose the change. So therefore what I say, current flows such that increase in current is opposed. Increase in current is opposed. Are you able to understand now? Understood now? So therefore this coil will try to flow current in opposite direction. Coil will try to flow current in opposite direction because it wants to oppose this current. But battery is very powerful, no? Finally current will travel in the same direction. So what inductor can do? Inductor can delay the rise of current. Inductor ఏం చేస్తుంది? కరెంట్ సడన్గా మ్యాక్సిమంకి రీచ్ అవ్వకుండా కొంచెం అపోజ్ చేస్తుంది. సో రైజ్ ఆఫ్ కరెంట్ ఈస్ డిలేడ్ సచ్ దట్ బట్ కరెంట్ కెనాట్ బికమ్ జీరో. Are you able to understand? But definitely it will reach maximum, but it will oppose for some time. Are you able to understand? That is the function of inductor. So immediately when current tries to increase suddenly, it will oppose the sudden rise of current. Similarly, it will oppose the sudden fall of current also. See, if I open this switch, what happens? If I open this switch, what happens? Current starts reducing from 5 to 0, no? And again, will it happen in suddenly? It cannot happen suddenly, no? So therefore, current starts reducing. So what coil will do? Coil will try to make a current flow in the same direction. Because again, it doesn't want sudden decrease of current. Sudden increase also it will oppose. Sudden decrease also it will oppose. That is the function of inductor. Are you able to understand? Now see. Now we will study about flux linkages. Okay, ma? Flux linkage. What is meant by flux linkage? Okay. Flux linkage. So it is number of turns of the coil multiplied by the flux which is linking the coil. This product is called flux linkage. Okay. So this flux linkage is directly proportional to amount of current which is flowing, no? If a small amount of current flows, small amount of flux is produced. More amount of current flows, more amount of flux will be produced. That's all, no? And now if I want to write a proportionality constant, that proportionality constant is called L. Okay, ma? Where L is called as inductance of the coil. Inductance of coil. So that is the inductance of this inductor. Okay. So L value, how can I write? L value I can write it as N pi divided by I. This is the equation of L value. Or how much flux is produced per amount of current which is flowing. That is called as inductance of the coil. Are you able to understand now? Now, what I can do, see. Now what is Faraday's second law? EMF is minus d pi divided by, or I will write minus n d pi divided by dt. This is Faraday's second law of electromagnetic induction. I will take n also inside the brackets. So minus of d by dt of n pi. N pi is nothing but L into I, no? Substitute. So therefore EMF is equals to minus d by dt of L into I. L you take out of integral differentiation, minus L di divided by dt. So this is one more equation to calculate L value. Okay, ma? So EMF induced is equals to minus L di by dt. So therefore from this I can get one more equation of L. Just will write L only. L is equals to EMF induced per change in current. This is another definition for inductance of a coil. Okay, ma? So what is E divided by di by dt? How can you define L value? What is E? EMF. Di by dt? Change in current. So EMF induced per change in current is called inductance. So you can define like that also. Okay, ma? So what is meant by inductance? Inductance is the amount of EMF induced per rate of change of current. rate of change of current. Are you able to understand now? That's it. See now. Now we are supposed to write a formula to calculate inductance of a solenoid. This is also an inductor also. You can call it as inductor, solenoid. Everything is same. Conductor wind in the form of a spring. Okay. What is the length of the solenoid? The length of the solenoid is L. Area of cross section is A. And N is the total number of turns which are present in the solenoid. See, small n is different. Capital N is different. What is small n and capital N? Number of turns? Huh? Capital N gato? Small n is number of turns per unit length. Per unit length, how many turns are present? That is small n. N is total number of turns. Okay. So, Sima. So, therefore, inductance of solenoid is given by L is equals to mu naught n square A divided by L. L is length of the conductor. Okay. So this is the equation to calculate inductance of a solenoid. Mu naught n square A divided by L. Okay. And here we are using capital M. Be careful here. We are not using small m. Okay. And we write a case. Case is that if a solenoid is wound on a core of permeability mu, then L is equals to mu n square A divided by L. This is the formula. Clear? So here, what is the core of the solenoid? Ikkada core edi. Core means the material on which we are winding the solenoid. On which material we are winding? Air. Air is the core here. Clear ma? Here who is the core? Air or vacuum is the core. But what you do, you take any material. For example, you take a piece of iron. On this iron, you wind this solenoid. Okay ma? Iron piece will have some magnetic permeability, no? That magnetic permeability I can call it as mu. Then this is the equation. And we know relative permeability is equals to mu divided by mu naught. Do you remember? Relative permeability formula, permeability of medium divided by permeability of free space. So therefore mu value, how I can write? I can write mu naught into mu r. Mu naught into mu r. So take this value and substitute here. Then what is one more equation of inductance of a solenoid ma? Mu naught mu r n square A divided by L. This is the equation to calculate inductance of a solenoid if solenoid is wound on any core of permeability mu. Okay? Right now. Sima. So next concept is mutual inductance between solenoids. Sima, just now we studied self-inductance. What is self-inductance? Self-inductance. Ade cheptaradu Umesh. Self-inductance means what? EMF is changing in the same coil. Flux is changing in the same coil. EMF is also induced in the same coil. That is self-inductance. But here condition is different. Here we are placing two coils side by side. This is first coil, this is second coil. Number of turns of this coil are N1, number of turns in second coil are N2. Now what I am doing, here there is a battery and here there is a switch. If I close the switch, what happens? Current starts flowing, no? So let I1 be the current which is flowing. I1, is it a constant? Initially. Immediately when you close the switch, I1, is it a constant? No. It starts rising, no? I1 starts rising. If I1 starts increasing, flux also increases. No? If flux increases, that some of the flux will go and link with the second coil also, no? Who is producing flux? First coil. First coil is producing flux. But some of the flux is linked with second coil also. That flux is also changing, no? And that flux is pi2. What is pi 2? Pi 2 is the flux which is linking both first coil as well as second coil. See, it will produce more flux, but only some flux will link with second coil. That flux linking is pi 2. The flux which is linking second coil also. So if current is a variable, pi 2 is also variable. No? If pi 2 is a variable, then EMF will be induced in second coil also. అర్థమవుతుందా ఏమన్నా? You are changing current, flux will change. That flux goes and links with second coil. If flux changes, EMF will be produced. So that kind of EMF produced is called as mutually induced EMF. Are you able to understand, ma? అర్థమైందా ఏమన్నా? So write down the statements. So I1 is a variable. Okay, ma? So magnetic flux is also variable. Okay? Sum of the flux links with second coil also. Links with second coil also. So if this flux varies, EMF is induced in second coil also. EMF is induced in second coil also. Okay, ma? This kind of EMF is called mutually induced EMF. Mutually induced EMF. Understood, no? Now here EMF is not because of current present in the same coil. It is because of current present in another coil. So that is why it is called mutually induced EMF. Okay, ma? Now see here. So flux linkage is how much here, can you say? Flux linkage in second coil is how much? Chapandi. Flux linkage in second coil. What is flux linkage? N into pi. N value anta, pi value anta. N value? N value of second coil antara? N2. Flux linking is how much? Pi 2. That's all. Pi 2 is the flux which is linking both of them. No? So N2 pi 2 is the flux linkage. Now this N2 pi 2 is directly proportional to current. No? Which current? I1 current or I2 current? Huh? I1 current only. Because this flux is changing because of N1. No? Are you able to understand? This flux is changing because I1 is changing. I2 came sambandham ledhu akkada. Are you able to understand? So therefore N2 pi 2 is equal to M into I1. So this M is called what? This M is called as mutual inductance. M is called what? M is called as mutual inductance. Are you able to understand? So therefore how can I define M value? M value is equal to N2 pi 2 divided by I1. This is one method of explaining mutual inductance. Are you able to understand? Now write the second law of right. Now write Faraday's second law of electromagnetic induction. EMF is equals to minus N d pi divided by dt. That's all, no? So N2 pi 2. So take N also inside the brackets. Minus d by dt of N2 pi 2. And N2 pi 2 can be written as M into I1. No? Substitute here. Minus d by dt of M into I1. So M, if I take outside, EMF is equals to minus M di1 divided by dt. Okay, ma? So this is another equation of relation between EMF and mutual inductance present between the coils. Okay. So how can I define mutual inductance? Therefore, mutual inductance is equals to EMF divided by di1 divided by dt. చెప్పండి ఇప్పుడు దీని డెఫినేషన్. డెఫినేషన్ ఆఫ్ ఎం. ఈఎంఎఫ్ ఇండ్యూస్డ్. చెప్పండి. ఈఎంఎఫ్ ఇండ్యూస్డ్ పర్ rate of change of current in first coil, not in second coil. That is called as mutual inductance. Are you able to understand, ma? So EMF is induced in second coil because of change in current in first coil. That is called as mutual inductance. Are you able to understand? Okay. Similarly, we write mutual inductance between two solenoids. Okay, ma? So, mutual inductance between two solenoids. Okay, Sima. So, this is a core on which we are winding two solenoids. This is first solenoid. Are you able to understand, ma? Through which some I1 variable current is passing. Okay. So on the same core, we wind one more solenoid. This is my second solenoid. Are you able to understand what is happening? For mutual inductance, there should be two coils, no? So I am taking two solenoids. One thick dotted line is indicated by one solenoid, thick line is indicating second solenoid. So here current is I1 and here current is I2. Okay. Then, okay, ma? So if current varies in one solenoid, then EMF will be induced in second solenoid. Are you able to understand? If current in one solenoid varies, flux linking with the second solenoid also will vary. If flux linking changes, definitely EMF will be produced in second solenoid. Okay. So therefore, mutual inductance between these solenoids is given by mu naught N1 N2 A divided by L. This is the equation. Okay, ma? Where N1 and N2, their number of turns of first solenoid and second solenoid. A is the area of cross section, L is the length of the solenoids. Okay. Now here we will write a case also. What can be the case? Case is what, ma? So if core, okay, Sima. So case is, Sima, here what is the core we are taking? Air. If air is taken the core, then this is the equation. Mu naught. What is mu naught? Permeability of what? Permeability of free space. Clear, no, ma? So instead of free space, if I wind it on some winding, then that medium has, that core has permeability of mu. Then I have to write mutual inductance is mu N1 N2 A divided by L. And we know this relation, no? Relative permeability is mu divided by mu naught. Mu of medium divided by mu of free space. Therefore, mu value is how much? Mu naught mu 1. So substitute. This is the equation to calculate permeability, mutual inductance when solenoids are wound on another core of permeability mu. Okay? గంగిగో పాపరే గంగిగో పాలు గరిటెడగిన చాలు అని ఆ టైప్ చూడండి. See, now we are discussing about inductance when they are connected in series connection. Next we will study inductor when they are connected in parallel connection. See, here inductors can be connected in two methods. One is series aiding and the next one is called series opposing. Series aiding means what? Polarity of the inductors is same. Are you able to understand, ma? So the EMF which is produced in this coil or the flux which is linked with this coil will be linked with second coil also, such that total inductance will become maximum. So mutual inductance will become positive here. That is, total inductance of the circuit will increase. That type of connection is called series aiding. Then in this condition, what is the equation to calculate total inductance? L1 plus L2 plus 2M, where M is the mutual inductance between the coils. Okay, ma? Now same what you call inductance, they can be connected like this also. Now see, the polarity is different. No? Are you able to understand? No? Dot is here, here dot is here. It means they are in opposite polarity. When they are in opposite polarity, mutual inductance will oppose the total inductance. There are derivations which we don't need them, just remember the formula. So L1 plus L2 minus 2M. Are you able to understand? So these are the equations when series aiding, inductors connected in series aiding, and this is series opposing. Clear? Similarly, inductors connected in parallel connection. Okay, ma? So inductors in parallel. Okay. Parallel connection means what? This is one inductor. This is another inductor. This is another inductor. So like this, consider 3 inductors are connected in parallel. Okay, ma? So by neglecting mutual inductance between them, okay, ma? So this is L1, this is L2, and this is L3. So therefore, total inductance 1 by L is equals to 1 by L1 plus 1 by L2 plus 1 by L3. So this is the formula to calculate inductors when they are connected in parallel connection. Just like you can say resistor connections. If resistors are connected in parallel, this is the equation we use now. 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Same formula here also. Clear, ma? That's it. So this completes our topic called electromagnetic induction.